Hello, everybody. We are the podcast named Zero Point, and we are happy to present ourselves. My name is Anton.
My name is Sasha. Good day, folks. 0 Point, interesting name.
Yep. So this podcast is split into two parts. First one is a mathematical one, and I am the speaker, the mathematical speaker. So today we are having mathematical part. And Alexander, what do you present?
I present some kind of computational sociology from the theory and the overall plan at some point to arrive at singularity between sociology and mathematics. Am I allowed to say that?
Yeah, for sure. So we want you guys to see one things from different perspective. Uh, but today we wouldn't go much into sociology, but rather we will make ourselves familiar with mathematical way of thinking. So this one might look a bit abstract, but please don't be afraid. Rather uh, try to like enjoy it because those tricky thoughts are actually what we want guys to share with you and to enjoy. Yes, so the topic of today's podcast, let me switch to the board, uh, is named Ordinals. And I've chosen this topic because it goes deeply into sets which are essential throughout the whole mathematics. So during our podcast, we will make our understanding of the fact that the whole mathematics is actually built on top of the set theory and how beautiful, elegant, and laconic it is. So let us first discuss what the set is, because everybody is familiar with the word, and you might even think that you're familiar with the concept. But as I'm going to show, it's not that trivial actually. Yeah, let's us enjoy the subtlety of the topic. So what is a set? Well, in our general daily understanding, the set is just some things together, right? So you can have like apples, one apple, two apples, but when you group them together, then they become like a single entity, right? So they're no longer like disjoint independent objects, but rather one whole abstraction. So we can think of five apples as being one single object named set of apples, right?
Can I add? Can I add?
Yep.
What is more set idea is recurrent to itself, so not only apples can be contained in a set but also sets as soon as they are single entities.
Yes. That is what we are going to discuss right now, actually. So, the first elegance we will face is the fact we actually don't need apples. We don't need to introduce any other like types of objects, right? We don't want this complexity. We want to stay simple. And simplicity is we only have sets, right? So let me introduce some notation that I will use throughout the whole video. So to denote a set, we use these fancy curly brackets, right? And if I write something like this, so bracket 1, comma 2 bracket, this denotes a set of two elements, namely 1 and 2. Simple enough, right? But as we've just discussed, we don't really need like some additional elements like numbers or fruits or whatever. We are fine with sets, right? So we can draw sets here like this, right? So this is a rather complicated set, but in some sense it is very simple because it only contains sets. And what I want to insist on is this guy here, and also, let me switch color, this guy deep there. So those are empty sets with no elements in it, empty. This one is usually denoted with this symbol crossed O, or whatever you want to call it. So what is an empty set? It is just a set containing no elements. You might think that it is a trivial object, well it is, but to make a possibility of like arguing about something, we need to state that the empty set exists. And this is a first axiom of a set theory. So axioms are those statements which don't need proofs, because they don't need proofs actually for two reasons. The first one is that we cannot prove them. Like, how do you prove that the empty set exists, right? And the second reason is that we are okay with such a statement. I mean, who would disagree with the fact that empty set exists, right? So okay, now we want to introduce another, like it is a fact, which is not that trivial to understand, but we will manage. So consider two sets. One is an empty set, and the other one second, please.
Yeah, let's
So,
take
so consider these two objects. They look similar, but in fact they are not. So the first one is an empty set, and the second one is a set containing an empty set. So I argue that those are different. Like, one might think that there are no elements in the first one, and so there are no elements in the second one because it just contains something with no elements, meaning there are no elements at the end of the day. But it's not the case, actually. Like, consider the analogy with boxes, right? You can think of an empty set as an empty box. But the box which contains the empty box is not itself empty, right? So out of nowhere, only out of like the existence of an empty set, we have constructed something which is not an empty set. The set containing empty set. Here this is where the magic starts to happen. Any comments so far, Alex?
Do we need any more axioms, or can we say at this moment that actually these two axioms are enough to form a notion of a number?
Good question. So there are additional axioms in the set theory, of course, but the need in them depends on your goals, right? So what we've used here is first existence of an empty set, and second, the ability of taking a set and putting it into the set as an element. That is what you have mentioned, that sets are themselves elements of the sets.
Do not we also presuppose that you can measure the length of the set? Let's say if we try to program that, is the function len say valid for these two sets, and for the two on the screen, the left one should give us 0 and the right one should give us 1 as an output.
Yep. Yeah, that's absolutely valid. So in set theory, we use the word size, or if you want to go fancy, you can say cardinality. So the cardinality is just a fancy way of saying the size. So this one is of cardinality 0 and this one is of cardinality 1. But just never mind. It literally means size. Yes, so we can introduce the notion of size, that's for sure, and it is actually an interesting subject to investigate. It can go tricky. Like in future series, we will overview the notion of infinite sets. So what you can say about the size of an infinite set, right? And also, do we care about duplicates in the set? Like, what do you think, Alex, if we consider a set containing two equal elements, like what's the size of this guy?
I don't know. If you ever managed to write that, I think the size is a 3, but in Python you are not allowed to create set with duplicates at all. So Python would say 2, but wouldn't accept the input.
Uh, yes, so some good thoughts said. Well, first of all, if we speak about the Python, it will allow you to add 1 to this set. So you have this set, right? And you say to Python, Python is a programming language for those who not much into programming. And of course, programming languages are capable of working with math objects such as sets. So if you ask Python to add 1 into this set, what it will do, it will literally do nothing. It will just ignore your request because of the fact that 1 is already present in the set. So from the Python perspective, there are no reason to have duplicates in the set, right? But you Alex, also mentioned this fact that I were able to write 2 once, and this means something. Let me go deeper into that. But it is a side branch of our discussion, so not really essential to ordinals. So we are having 2 ones here, right? So don't be confused. Don't confuse the abstraction of 1, like the ephemeric entity, which we all familiar with, and its instantiations. Like there is a notion of letter A, right? But I can make multiple instantiations of this letter, like this one. Here is the instantiation. Here is the instantiation. I can type it, right? This small letter. So there is a difference between the abstraction and the entity representing it. So when we are talking about the sets, it is an interesting question whether we are talking about the abstraction of a set or the real instance of it. And that is also true for elements of the set. So here, those two ones are definitely two distinct instantiations. So in that sense, they are different. But those are instantiations of one abstraction, which cannot be duplicated. Like you cannot come up with a second abstraction of number one, right? It is like by definition, I don't know, by the reasonable sense, like common sense, it is single, but can have several instances.
Can I ask a tricky question?
Of course, we're here for that.
Is there a system of numbers like 10 digit or 2 digit that, or is there any possible one that does not contain the number one in it?
Well, there is a way to write numbers with so-called unary language. I'm not sure if your question is about that, but like, how do we write numbers usually? We usually use digits, right? For example, this is number 123. And so I've just used 3 digits to represent quite a big number, right? But the very naive approach would be just to use some symbol, let's say dot or star, right? And so I represent the number by just putting the corresponding number of stars. So this is number 5. Was your question about this kind of stuff?
Yeah, but in this sense, the star is a only digit in the system, so it's a one digit system, and star, so to say, represents one in that simplest system.
So can we, but how, okay, like how would you represent one in your notation system, right? So
So
if you are able to represent it somehow, then you can use this representation as a definition of representation of one, right?
all right, but I think one is present in any system. Therefore,
I've just tried to prove that. Like assume the system does not contain one, but it is representative, meaning you can represent one in it. So you can take this representation of one as a representation of one, basically.
all right. So
Yeah.
actually, this idea of one is born when we say that empty set and set of an empty set are different objects because their lengths are different. Come on.
Let me think about it. Yeah, I think you need something when you have distinct objects, right? To distinguish between those. So it is really important that we can have different sets. And so, yeah, one of the ways to see that sets are different is, for example, to compute their length, which would be different. So if some two objects have different properties, those objects are different, right? That means that in set theory, we have different objects, which is quite important, I mean, from the philosophical perspective.
Yeah, indeed.
Okay, so let us continue with ordinals. We didn't even start with them. But before I do that, I need a notion of contains. So this symbol is read like contains. And we usually want to talk about which elements does the set contain when we are talking about sets, right? For example, this line here can be read as this set 1 and 2 contains 1, right? So I have object is in the set, or the set contains object. Okay, so yeah, if you read it from right to left, it is read as contains, but if you read it from left to right, it is read as in. Simple enough, I think. Okay,
And it
so let us
gives,
build. Excuse me?
yeah, and so that contains symbol, it gives true or false. And
Yeah,
if true, then you can just write it. So the phrase one is in set 1 and 2, it is true. So you just write that.
yeah, for sure. So, for example, here we have uh, the correct statement, and here we have an incorrect statement, but both of them are valid. In a sense, you can write them down, right? But probably they won't be true, but you can write them. Okay, so let us introduce the first ordinal in your lives, probably. And what is that first ordinal? Dear viewers, you can guess. And Alex, you can also guess what is the very first ordinal.
It's an empty set.
It's an empty set, of course. So
What else?
empty set is actually an ordinal. And what is the second ordinal?
A set of an empty set.
Right. Right. So you guys might think that the third one is a set of an empty set, so that I will just draw another brackets here. But it's actually not the case. So the third ordinal is a set containing first two. So it is a set which contains first ordinal and which contains second ordinal. So the fourth ordinal is one containing first ordinal, second ordinal, and third ordinal. So what I can do is I can select all those, copy paste them, and put them into set, and that would give me fourth ordinal. Right, so this procedure, like to build the feeling of what is happening, is essential for understanding ordinals. And let me repeat it. To construct an ordinal, you just take all the previous ones and put them in a set. That's it. And so, like as a quick remark, for those who are like curious and who don't believe like anything that I say, which is a good habit, by the way, those might wonder, like, okay, to construct an ordinal, you need a notion of previous ordinals, right? Because you need to collect something into the set. So what do I do with the very first one? There is no like previous for the very first one. Yeah, so that is why it is an empty thing. There are no previous, so the set of all previous is just an empty set.
Wow, yeah, that's actually beautiful.
Yeah. Mm, okay, so and as you guys can imagine, we can do that infinitely long if you have time and nothing to do. You can construct ordinals. Um, but here is the time for us to jump over infinity. So you can construct fourth ordinal, fifth ordinal, sixth, 100th, like 1 millionth ordinal, and so on, so on. But each of them, in particular, is finite, right? So 1 million is a big number, but it's just a number, right? It's something finite. How do we construct an infinite ordinal? Well, it's a question to you guys and to you, Alex. Like, what would be the first infinite ordinal?
The first, um, I have some desire to say that it is an empty set, but I don't have a reason.
No, wouldn't work for the second time.
Also, should it contain itself or not is a question.
We'll get back to that.
Mm, maybe it's just impossible to construct an infinite ordinal.
Good guess, creative one, but in fact it is possible. So, and the way we construct it is very, very in the nature of ordinals, and at the same time, it is not something new. So the first infinite ordinal is just a set of all finite ordinals,
Yeah, that's true.
right? Like pretty simple. So let me do some rearrangement. So we have this finite ordinals, right? Written in the line. And so to construct a first infinite ordinal, I just put all of those into the set. And this set is infinite.
We cannot write it at one line, let's say, at any of the existing places, actual places, but still we can construct any element by its number, for example, in that set.
Yeah. Yeah, so it is like semi-constructive. And that is actually the very good feeling of infinity. Like you cannot really write down the set of all natural numbers, for example, but you can write any of those uh, by itself, right? And so here things are starting to get tricky, but thus interesting. Um, and I want you guys to question yourself at each step we do. Like, why is that possible? Don't we produce some nonsense by doing that or this? And if yes, why? If no, why? So this is like a great mathematical exercise for you. And for those who just want to enjoy the show, let us continue building ordinals. Like what would be the second infinite ordinal? What do you guys think, and what do you, Sasha, think?
I think it's a set that contains um, infinite ordinal.
So the only element.
Yeah, I guess so.
But then, a great question for you guys to ponder. Like if a set contains a single set, which is in its turn infinite, is the set, the outer set, infinite by itself? So let me say that X is an infinite set, right? And so consider the set which contains X. So is this one infinite? Or in
Well,
other words, like what is the length of this set? What is the size of it?
yeah, I think that's enough to just write infinite set in a set because infinite set should theoretically include all the possible ordinals.
Oh,
But
well, no, we are
yeah,
not yet speaking about all the possible ordinals. That's we are not ready for that. That
okay.
just yeah. What do you think about this question? Like this set, which contains X as an element and X itself is infinite. Is this set infinite or not?
We actually jumped into this notion of infinity, but what notion we already have is a notion of length, which can be used on sets, as you told. Therefore, a set of X is of length 1 because it basically contains one entity. And if that's infinite, by infinite you mean infinite length, and length is that function, then no set of infinite set is a set of length 1.
Yeah, yeah. So good observations. I mean, I agree with the first argument that this set is actually not infinite because it contains the single element. Like, what's the size of this set? The size of this set is one. One is not infinity, right? Yeah, great. We stumbled upon this nice beauty. Uh, but back to my question, like, what is the second infinite ordinal? As we just pointed out, if you just take a set of this big guy, this would not be itself infinite. It would be of size 1, containing only one element. So how do you construct the second infinite ordinal?
Well, then the set of all finite ordinals and also an first infinite ordinal.
Absolutely, absolutely. And I want to underline that we are doing nothing new here. So how do you construct the ordinal? You take all the previous ones and put them in a set. That what you just did, Alex. You took all the previous ordinals and you put them in a set. But those previous, they consist of all the finite ordinals written here and the first infinite ordinal. Yeah. So, uh, and so on, I wanted to say. Like, you can do that infinitely many times and like infinitely many because Okay, let me denote this big guy with omega. So this is omega. And if you take all the uh, finite ordinals and omega, you get omega plus 1, y plus 1, because we just applied our operation of constructing ordinals one more time, right after we've obtained omega. The next thing we have obtained is omega plus 1. So kind of reasonable notation, but of course it's not uh, any way in any way connected to like integer addition, right? It's just the way to represent what we are doing. And of course we can apply our operation like one more time, and we will get omega plus 2. Then we can get omega plus 3, and so on and so on. So what I think would be in the end of this chain?
Infinity, no?
Well, you need to be more precise because everything now is infinity. So we are now we are swimming within infinities. So we made this jump right by taking all finite ordinals, and that gave us an access to the world of infinity. So
All right.
now we are just playing around with infinities.
Then I guess it's 2 omega.
Yep, absolutely. So why 2 omega, right? Because what you will end up with is just making this omega times, so to say. And it's reasonable to denote this with 2 omega, right? In some sense. Okay, so we can proceed, right? And build another like second order infinite chain, uh, this time in a column. So we have 1 omega, then we have 2 omega, then we can uh, do all this stuff once again. We will get 3 omega, and what would be the end of this chain?
Omega times omega.
Absolutely. Oops.
Or omega squared.
Yep, exactly. And so you can go like crazy with these operations. This is like second order thing, but you can even jump to the third order thing by doing all this stuff once again, like omega, omega, omega times. And what you will end up with is omega to the power of omega. Uh, and actually, you can build those exponent towers, so they're called. So, like omega to the power of omega to the power of omega. And guess what's next? Like,
Hmm.
how do you proceed? Yeah, it's a very tricky one. So let me give you a hint. So this is an exponent tower, so it is called.
Maybe just add 2's to all omegas. Sorry.
Yeah, but that wouldn't be like a categorical jump. I think you agree. So the next thing to say is actually that we are saying that the height of this tower is, what I think it's omega, right?
Yeah,
And
it's like a Rick and Morty adventures. We got into the world of omegas.
yeah, yeah, absolutely. So for each like new notion, uh, you can say, well, what notions do we have here? Like we have addition, then we have multiplication, then we have an exponentiation, right? So for each such notion, you can say that, okay, I will do that omega times, and that will bring you to the next level. And guess what? Now you can say that there are omega such levels, and you're like on the meta level of the universe. I don't know how to say it in another way. It's just crazy.
And that began with the two things: nothing and an empty set. Boom,
Yeah,
and
yeah,
start.
yeah. So this is like the beauty of the math. You are just sitting, watching this show. You're doing nothing, but inside your brain, universes born. Yeah, so beautiful. And not only you can admire them, but you can explore them. You, in some sense, you create them. This is a big philosophical question, actually. Do we create math or do we explore it? Let us guys know in the comments what do you think about it. And Alex, what do you think?
Mm, I think God created math, and people they at the same time create it and explore it. Mm, yeah, because infinity contains everything possible. Let's say everything ever possible. And yeah, I kind of bought that idea that when we actually write down, that is an instantiation, while the what we are writing is already contained in a set of all the finite meanings of that. Yeah, and therefore, so that's a role of human to instantiate. The role of God is to kind of give opportunity.
Yeah, like I mean, reasonable position. No, nobody would like prove you're wrong, right?
Yeah. But
Uh,
there is so there that is a ladder high. That is a ladder high into metaphysics, let's say. But what about ladder down?
mhm.
Can we also from this point when we created ordinals somehow arrive to the laws of physics, or I don't know how we use math every day?
Okay, that's a good challenge. Let us let us try. I mean that this refers to our ability to generalize, um, right? Because what we were doing, we were like following the same rules, but in a different context. Like I started with just creating third ordinal by taking first one and the second one, right? Uh, and it's not general yet, but then I moved to the formulation, which is more general, less specific. I said that didn't I took first and second, but I took all the previous, which is, in the example is the same thing, right? But the letter formulation is generalizable. Like, because having it, I can construct a fourth ordinal by taking all previous, right? So let us both think of like a daily life example where we apply this kind of generalization.
I don't know, I think any kind of metric in time is a kind of generalization like that. Anything that adds new information should remember the already gathered ones. But ordinals, they also tell us how did they arrive at what they seem to be, because they contain, all the sequence from the first element to that ordinal. So I
Yes.
think
So
ordinals
mhm.
are basic of repetition, and kind of the first order, let's say, or progression.
Yeah, we will we are just about to discuss why are they actually called ordinals. But before we will dive into that, I just came up with an example from my personal life. So I'm now staying in Switzerland, and in Switzerland, shops are closing at 7 p.m. And this is a general rule, but how did I know about that? Well, I went to the supermarket called Migros, and I was late, so it was closed. And I read the sign saying that, okay, we work until 7 p.m. So what knowledge did I extract out of that? Well, not that the single Migra instance is working up to 7 p.m., but probably all Migrases are working till 7 p.m. And another jump, like all supermarkets work until 7 p.m. And probably another jump, like um, most of the organizations work until 7 p.m. Right? So this ability of going through from the particular instance to the general rule, and then applying this general rule back to something, because when I have this general rule that most of organizations work until 7 p.m., I can now say that, okay, probably up pharmacy shop works until 7 p.m. And I deduced that by going up the ladder rule, starting from my instance of Migro, and then going down by applying this rule to pharmacy. Yeah, that's how, like, it is so complicated when I'm saying that, but this is how we humans think, right?
So let's once again discuss that kind of step on the ladder. So when you face that the shop is closed, you probably thought that you are not the only one who stuck into the closed Migros, and you thought that some people might have thought about providing you other solution. I think that would be also a, a step from the plurality of closed Migros to the plurality of occasion of person not being able to shop.
Yeah, and when you were giving this example, I thought that we are actually operating with facts themselves. Quite rarely, we immediately jump to some generalizations. Uh, yes, we are not living in this universe of raw facts, but we want to somehow systemize them, right? Yeah, cool. So let us now discuss why ordinals are named ordinals, finally. So ordinals, the name ordinals actually comes from the word order. And this one is closely related to sets because you can order sets. And this refers us to the question whether the math is discovered or invented. Like, let me ponder a question. Okay, for example, I have this set, and I have this set. which one is bigger?
That's kind of choice between obvious and controversial.
Yeah,
Yeah,
yeah, but yeah, my take is that it is really, really wonderful, amazing, and surprising that the answer is in fact obvious. Like, imagine a human, like a guy who's watching this video and who previously knew nothing about math, nothing about set theory. Even for him, this answer is obvious. So it kind of pre-exists in some sense, right? And we just need to point it out. Isn't it mysterious? I find that it is.
yeah. I think mysterious is a good word because they, I think, some tricks to make it think. For example, let's say, and so the set on the right is bigger. It can be at least because it contains one and two, and also contains something else, which is, I think, a good definition of being bigger. Um, yeah, but when we swap, let's say, when we swap one and two, maybe the rate would a bit fall. If we like say that it's 11 and 12, also raises some question and so on. Or if it is 1 2 1 2 minus 5 minus 10, what about that?
Now I think you would agree that the letter one is not that good of a take because when we are talking about sets, we don't really want to dive into the nature of the objects, right? So what you've tried to do, you tried to reduce the comparison of set
No.
to the comparison of elements. So you introduce negative numbers, and negative numbers are smaller than positive, and you try to take this smaller and bring it to the set level. That's what you are trying to do. And actually, this is studied by the branch of mathematics called category theory, which we will probably overview in some future series. But for now, let us just state that we don't want to go into the nature of the elements. Namely, we can imagine those are just colorful balls, right? So you have orange ball, blue ball, red ball. You cannot compare them. You can do nothing with them. They're just distinct or the same. This is the only thing you have. So yeah, the good question is like this set containing number 3, is it really smaller than this one? So the one answer is yes. The second answer is no. Let me argue for both of them. So the first one is yes. Why? Well, because the length of this set is bigger than the length of this one. Uh, and this is the way to reduce the comparison of sets to comparison of numbers, right? We forced, like, see, we need to compare two sets, like S1 and S2. We want to put one of those 3 signs here, right? So it's either equal, less, or greater. So to put one of those, what we do, we go to another universe which we are comfortable with, namely the universe of numbers. And we travel there by using function len, uh, which transforms the set into the number by computing its size, basically, right? Its length. So for example, the length of S1 is 1 and the length of S2 is 4. And here we have no doubts, right? We know that 4 is bigger than 1, that's it. And then we go back to the universe of sets and we say, okay, we then deduce that it's the same sign here. So this is like the way we think about it. We go to another universe. There the order is well defined. We use this definition and we go back, just bringing result with us. So let me point out that this approach is actually not that good. Why? Because when we move to another universe, we lose information. Like, set is an informative object. It tells you something about the elements it contains. But when you reduce it to its length, you no longer have an information about the elements. You just lost it. So this reduction is not fair for some sense. And this is the disadvantage of the discussed approach. And so mathematicians were choosing either we can easily compare any two sets by just computing their length, or we refuse to compare all pairs of sets. And because of the fact that comparing by sizing is a weak thing to do, mathematicians decided to agree on the fact that we cannot compare any two sets. And that is something new, but also it is not new at all for us. Let me just bring a real world example. So here, like in our abstract mathematical world, we can say that this set 1, 2 is smaller than 1, 2, 5, 10. And at the same time, we cannot compare the set containing 3 with the set 1, 2, 5, 10. And it's this order is not total, so we cannot compare any two pairs. And that is true. Like, total order is a very rare thing to face in our world. Like, for example, can we compare humans? Like, you can compare their heights, you can compare their salaries. I don't know, you can compare their age. But what if one man has a height of 1 meter 80 centimeters and another has a height of 1 meter 90? So the second one is taller, but he has a smaller salary, right? How do you compare them? So you can probably imagine like two humans which are comparable. It's a hard thing to come up with. Another example would be price and quality comparison, right? So you have lots of stuff sold in the supermarket, and you come to the shelf, right? And you take 2 packets of crisps, for example, and you know that the first packet is of natural, good quality crisps, so we want them, but they are more expensive than the second packet, which is not that natural, probably some chemicals there, but it's cheaper. So those two are not comparable, right? We cannot do that. The order is not total, but at the same time, you can probably find two packets of crisps for which you can say that the one is strictly worse than the other. And here where economics kicks in and say that, well, the second one would not survive on the market, so the market system ensures that products are not comparable, in fact. And this is a link to economy and thus sociology, I suppose, what I think.
Yeah, it's not only a link, moreover, I disagree. So, yeah, there is obvious something into economics. Uh, yeah, I wanted to add maybe some examples from social sciences, how this impossible total order is getting theoretically addressed. Now, well, first of all, to compare humans, you refer to a class theory, which presumes that a society persists in some kind of order of these horizontal groups of humans who don't even know each other or had an ability to talk, but still they share this property of social class, which are on the hierarchy of classes. And there has been as many names as approaches, and yeah, I think you know some examples, but actually some system of classifications then started to appear with reference to occupation status or levels of different capitals and so on. And so that system in its perfect form would be as complicated as society, but it needs to keep simple. So therefore 11 categories or 9 categories on this occupational statuses get involved. So it's not all the time binary, but also it can get more complicated, which reveals that actually such a representation is a loss of information. Well, as any sociological grant theory, I guess. And also that thing with the products, it's called utility and economics, and that's also a function that you can take some economic goods as an input in and get how much pleasure on an integer or on a quantitative scale they deal to you, let's say. Um, so it, so both sociology and economy are addressed, and not in all parts successfully.
Yeah. So it's interesting that we lose information when we try to go to the total order. I mean, this is the common takeaway, I suppose, from this subsection of our talk. Okay, so let us proceed with ordinals. Um, the thing is, ordinals are called ordinals because they can be ordered. Like, for example, let me draw down this second ordinal and the third ordinal. We faced them some time ago, so we should be familiar with them. Okay, so which one is bigger? Uh,
Uh, the one on the right.
the one on the right, yep, and I can define it like strictly because uh, for example, you might have came up with this answer because it's just literally syntactically or like graphically bigger. But the thing is, if I small it down, right, it is still bigger. Uh, so we want some rigorous mathematical definition of what is bigger. And actually, we don't need to introduce anything new, but we just need to recall that we have this nice in sign. So why the one on the right is bigger is just because it contains one on the left, right? So here it is hidden. Well, not that hidden, but it is present. The smaller one is present in the bigger one. And that is an essential property of ordinals, which basically holds for any two of them. So why? Why is that? Because we were constructing them one by one. So, for example, why can I compare fifth ordinal with the second ordinal? Because fifth ordinal is simply defined by the set which contains all the previous ordinals, thus it contains second ordinal, and thus it is bigger.
Yeah.
Do you see this line of reasoning?
It is Ordinal is very honest in telling who is bigger than him or her and who is smaller. In this case, fifth ordinal just shows by the only real content of it, which is itself, yeah, the mathematical notation behind. It tells that it contains a second ordinal. So I wanted to grasp that you don't need to bring two ordinals together to say which one is bigger or smaller.
So we defined the word bigger by replacing it with the word contains. That's just it. Okay, so the other thing we need is that ordinal is actually not contained within itself, right? Because it is a set of all previous ordinals. So it is itself not contained within itself, so to say. And I can write it down like this. I hope you guys agree with that. And this is sufficient for us to finally get to the topic of our podcast and to present the, now I need to find the appropriate word, let's say a bunch, a class of objects which cannot be a set. So, and this is the question for all of you guys and for you, Sasha. So what objects do we need to consider to state that all of them cannot form a set?
What property should it have?
No, I mean, you can give just a concrete example of such a class of objects. What are those objects which do not form a set?
Yeah, it's those that we are not sure if the set itself should be among those objects. At least that's the class of such. It's one of the class of such classes of objects. So actually, just unconsciously. Well, it's not unconsciously. It's thoughtfully. I thoughtfully produced an origin.
Yeah, exactly. So we need this self-reference to prove that something is impossible. And the answer to my question is, well, the class of all ordinals do not form a set. That's why I have introduced them. Okay, let us prove it. And the proof is very short and very elegant. And it is a proof by contradiction. So suppose ordinals form a set. Oops. Just a second, please. Suppose ordinals form a set. Okay, so we can consider a set of all ordinals. It will look like something like this. So first guys, then all the finite guys, then omega, then others. Like somewhere there would be omega to the power of omega, and like all those guys we've mentioned and many more. So this is the set of all ordinals. What can you say about this set? Does this construction of taking all the ordinals remind you of something?
All the finite ordinals, we have taken them.
Yep.
But
And
this ordinal contains even infinite ordinals.
yeah, so this one contains all the ordinals by the assumption. It's the set of all ordinals.
And we are unsure if it contains itself.
Yeah, that's the main point. So, but before saying that, we need to say the following. Like, if it is a set of all ordinals, it is the ordinal itself, right? Because how do we construct ordinals? We take all known to us already and we group them. So if we consider all the guys known and we group them, we get an ordinal. And thus this thing is ordinal. And here we get to this question of whether it contains itself or not. Well, it should contain itself because this is the set of all ordinals and it is an ordinal, so it should be in that set. So let us call this thing X. So we state that X is contained in X. But this means that ordinal X, by our definition, is smaller than the ordinal X, which, as we have shown, cannot be the case. So we derived contradiction, and hence the initial assumption was wrong. Therefore, ordinals do not form a set.
Just don't do that. I wanted to comment about the repetition of ordinals. So I wrote this word repetition in my conspect as an association with the word ordinal. That's a sequence that repeats itself. And at the same time, this sequence does not um, contain itself. And what I wanted to, and the word repetition, it jumped to a track which is called repetition. I'll send that to you. And that is electronic music, and I'm not a big fan of kind of repetitive, simple sounds for some reason. But I had an ability to reflect upon that, and actually that what I consider to be monotonous sounds are actually different sounds because they have number, at least if that is a set of all bass drum kicks, each one is a number of itself. And as we perceive music as cycling because of the time patterns and how we represent that in our on our notation, let's say, but actually music is not at all cycling.
Yeah, every node is unique if you consider its order, right?
Yeah.
Cool. So I think it's time for us to finish our session. So just to summarize what we've studied today is we introduced the notion of empty set, which is an important one. Actually, everything, like more than 1 hour, we just discussed the consequences of having an empty set. Then we defined the ordinal, which was constructed by taking all the previous ones. We discussed the order notion, which is a fundamental notion in mathematics, deeply studied. So, and the main takeaway for today would be that some orders are not total, meaning you cannot compare any two objects, like crisps in a supermarket, for example. And in mathematical terms, not any two sets can be compared, but ordinals can, and therefore the name. Ordinals are ordered. That's what we have proved. But they are ordered in a way that ordinal is not smaller than itself. And that fact helped us to prove the main theorem of today and probably of this month or this life, that there are classes which do not form a set. And one example of such class is a class of all ordinals. Yeah, that's it. We thank you guys for listening, for staying with us. Please let us know in the comments what are your thoughts, what do you want to hear from us. And we will see you in the next podcast, which will be about sociology.
Yeah, let's get in touch. Thanks for watching.
See you.